Okay, students, in this video, we're going to go through an example. We're going to calculate the charge of a solid sphere. But the purpose of this example is to remind you guys or review how to transform to spherical. And actually, I'm going to put cylindrical coordinates in here too. And this is associated with the first section in the first chapter of the book, reading 1.4. So I recommend you guys go through and read that as well. Okay, so let's get started. The question we are going to answer in this example is pretty simple, really. Okay, what is the total charge of a sphere with a radius of r, okay, with a charge distribution rho sub r, okay? And later we'll actually simplify that a little bit, but we'll keep it kind of general for now. All right, so this is our task. The first thing that I would do if I got a problem like this would be like, all right, I'm just going to draw a picture of that. It gives me a little something to do while I'm thinking about how to solve the problem. Okay, so I'm going to draw my coordinate system here. And let's see, I will draw a sphere. And I'm going to make my life easy. And the best I can represent it here. I'm going to center that sphere on the origin of my coordinate system because doing anything else would just make your life harder. Okay, so we'll call that good. I'm going to draw, actually, I'm not going to call that good. Make that a little bit more spherical. Okay, I'm going to indicate the radius of this sphere as given is that big R. Okay, and this sphere has some charge distributed throughout its volume, okay? And the goal here is to figure out the total amount of charge in the sphere. So to do that, I want to basically sum up all the charge distributed throughout this sphere, right? One thing I could do is break it into little bits of volume and figure out the charge of those little bits and add it all together. Or a more precise way to do it, if I have a continuous function describing how that charge is distributed, is to do an integral. So I'm going to do a volume integral. Okay, so I'll put a little v down here. And I'm going to integrate over this rho sub r. I'm going to put an r here. Oh. Okay, and I'm going to integrate over the volume. If you remember d tau, that was our a little infinitesimal volume here. Okay, and this, if you remember, that's our charge per unit volume. Okay, so that's the charge per volume. Okay, so that could be some function that depends on x, y, and z, or r. Okay, or it could be a constant. It just depends on the problem. All right, so the way that I have my coordinate system defined, you might think, all right, let's just go ahead and do this in good old Cartesian coordinates. Okay, so that would mean that rho could depend on x, y, and z. All right, and then, all right, to integrate over a sphere, I'd have to integrate over my 3 dimensions here. Okay, I want you guys to notice, right, the units of these infinitesimal lengths are all meters, so this has units of meters to the third. That's good, because this has units of charge over volume. So when I multiply these two things together, I'll end up with something that has units of charge. That's what I'm looking for. Okay, but this actually isn't a very good way to solve this problem. And one way you know that you're heading down the wrong path is that you're stuck, okay? If I look at this sphere, right, in order to do this volume integral, I need to define some limits. Okay, they're going to allow me to basically scan over the volume of this sphere. Well, in the x, y, z coordinate system, it's pretty tough. It's tough to figure out the limits, okay? So it's hard for this particular problem to determine the limits in Cartesian coordinates, right? It would be a different situation if I was dealing with a box or a rectangle or something like that. In that case, it would be easy to determine the limits in Cartesian coordinates. But for a sphere, it's hard, right? Because the surface of the sphere, right, isn't following any of the axes of my coordinate system. So of course, we're going to change it up a little bit. And it makes sense when you're dealing with a sphere to use spherical coordinates, okay? And you guys should have some experience with spherical coordinates from your math classes. Okay, but first let's just go ahead and define the parts of the spherical coordinates, the components. Okay, so spherical coordinates, that's another way for me to say, hey, that's where this point P is up here. So I'll just call that P. Well, no, I'm not going to call it P. That might get confusing. Okay, so one way I could define in a coordinate system the location of that point is I could say, all right, I still have the same origin. It's a distance r from the origin, okay? So over here, we're defining what spherical coordinates are. Our first coordinate is r. That tells me the distance from the origin. Okay. Of course, that's not enough to really specify where this point is in space. I also need to know, right, where it is along the sphere. Okay. So I can define another angle, and this angle I'm going to call theta. Okay. And theta is the distance from the z-axis. Okay, and that's still not enough because really if that's all I had, it could be anywhere along this ring here. So I need one more quantity to precisely define where this object is. In order to do that, I'm going to project this point down into the xy plane. That's what I'm doing here. Okay, and then I'm going to have one more angle that I'm going to use to specify the location. And that is phi here, okay? And phi defines the distance, okay, from the x-axis. I'm going to transform my volume integral, okay, from the Cartesian coordinates to my spherical coordinates, okay, and that's going to make it easier to solve. So basically that means I'm going to take x, y's, and z's, and I'm going to write them in terms of our new variables that define the position, r, theta, and phi. Okay, so again, I'm going to copy this picture over here. I just need to figure out how these quantities are related. The r one is pretty straightforward. Hopefully r is just going to be in 3 dimensions, x squared plus y squared plus z squared, square root of that. That's the length of the r vector in terms of Cartesian coordinates. Okay, and now I need to kind of look at the geometry of my picture. Okay, z is right this distance here along this line. So if I use a little bit of trig, right, that's the same as this distance here, okay, I can say that z is equal to r, which is the hypotenuse of this triangle, okay, r times the cosine of theta. Okay, that one's not too bad. The other two are a little bit tricky, x and y. Okay, so now we got to look at our picture a little bit more. And the trick for figuring out x and y is to actually figure out the length of this guy first, okay? Because if I can make a little triangle in the xy plane that looks like this, or one rather that looks like, let's see if I can make that like this guy here. Okay, and this is another way, right, where I could define the x and the y position in that plane. Okay, so the trick is I got to figure out what the length of this projected line is first. Okay, so I'm going to make this a different color so it's clear. This is the line we're worried about here. This line has a length of r times the sine of theta. Okay, it's the other side of this triangle here, same thing as that length. So now I know the length of this line, and I can make a new, this is the hypotenuse of a new triangle that is projected into the xy plane. Okay, so using that, I know that x is equal to, same color, being a little, x is equal to r sine theta. That's the hypotenuse of the triangle. And now I want to take this side here, that adjacent side. So I'm going to take the cosine of phi, and then the other one is r sine theta and the other side. Okay, so usually you don't put the parentheses, so you end up getting r sine theta cosine phi, and then r sine theta. Oops, sorry, I made a mistake right here. This should be phi, not theta. Sine of phi. Okay, so hopefully that makes sense to you. So that means, again, if you've got something like this charge distribution written in terms of x, y, and z, you're going to replace the x, y's, and z's with what they are in terms of our new coordinate system. Okay, so these quantities here. Okay, now we're not quite done yet, though. We've got to transform both what we're integrating over, okay, and the limits of our integral. If we already define the limits, we haven't in this case, okay. So let's think about what we're integrating over. So we're trying to integrate over little infinitesimal bits of volume. So in Cartesian coordinates, right, that would look like a box, right? That could be our little infinitesimal bit of volume, which we're calling d tau. Okay, and we can integrate over this. We can say that d tau is equal to multiplying these infinitesimal lengths, okay, where this could be dy in our coordinate system. This would be dx, and this would be dz. So we could vary these quantities, right, and we could end up integrating over a volume. Okay, that's how we integrate in Cartesian coordinates, okay? So if I integrate over dx, dy, dz, so basically resubstituting the d tau with these things, we're going to be tracing out a volume in space. Okay. Does that mean that I can just take then these guys in my integral and replace it with just dr, d theta, d phi? Let me actually write those as what they should be, actual d's. Okay, dr, d theta, d phi. Well, no, okay, it's not that easy. No. Okay, for one thing, notice that the units of this are the units of volume, meters cubed, right? Because each one of these has units of meters. Multiply them together, get meters cubed. This would have units of just meters, okay? So that can't be right. And you know it's not right because the units aren't correct. And this is always a good check when you're transforming an integral. When you take, right, this part, and if the units aren't correct, then you've done something wrong. You need to think about it again. All right, so let's think about how we can replace this part of our integral here. This part was something appropriate for spherical coordinates. We got to do a little bit of deep thinking in order to do that. So we're trying to trace out a volume, part of a sphere, okay? So let's think about how we would do that, okay? Part of a sphere, instead of looking like a rectangle or a cube, it would look like a little chunk of sphere, a little, you're going to take a little piece of the arc. Let's see if I can draw this very well. This is when my drawing gets a little questionable. Okay. You're going to take a little piece of this big sphere, this bit here is going to be, right, a little bit of that angle d theta. Okay. This bit here is going to be a little piece of the radius, dr. Okay. And this bit here, that's a little chunk of the arc that makes up a circle, right? So that can be r d theta. That's how you would, if this is d theta and the position of this chunk of sphere is at r, then the length of this particular bit here is going to be the arc length, which is r d theta. Okay, so we're just trying to figure out how to trace out this sphere. We've got two of the dimensions. This is dr, that has units of length. This little arc has a distance of r d theta, that has units of length. So really we just got to figure out this length here, this little side here. And that's the trickier one, of course. Okay, so we got to draw another little bit of a picture. And let's see if I can do this well. We're going to do something. No, that's not great. Okay, so we're trying to figure out the length of this guy here. Okay, this, I want you to think about a big circle going around like that. Okay, so think about it like a ring inside the sphere. This little distance here is an arc along that ring. Okay, so the ring, this big circle, that has a radius that's defined by this line here. Okay, and then instead of having d theta, the little angle here that's being traced out along that circle, which is going to define our arc length, is now d phi. Okay, so I just need to figure out the length of my radius here. Okay, that's similar to what we did before. It's going to be r times the sine of theta, right? Where we remember that this angle here is the angle theta. Okay, and this picture is getting a little messy. I'm not the best at drawing these, so I'm going to post like another image in the next slide just so you can take a better look. Okay, but this angle is theta, right? We got this distance r, so the length here is going to be r sine theta. The little bit of, in order to trace out a little arc length here, I need to trace out a little arc of angle, which is going to be d phi. Okay, so this distance here of this length is going to be that radius of this circle. Sorry, I'm being real slow here. This circle, which is going to be r sine theta. Okay, but now it's going to be d phi. Okay, so now these three distances, if I multiply them together, I'm tracing out a volume, a little piece of my sphere. Okay, so really what I want to do when I transform this integral, I'm going to replace this bit with a new way to define a d tau. Okay, and our new d tau, this whole thing, right, is a little bit of volume, which I'm calling d tau. Okay, it's going to be dr, right, and then it's going to be that r d theta, and then it's going to be r sine, sine theta d phi. Okay, and it's pretty unusual to put these parentheses. I just put them in there so you can kind of see the different parts of it. Okay, and then just to simplify that, you'll often see it simplified, okay, as r squared sine theta dr d theta d phi. Okay, so oftentimes you guys have probably used this before, and maybe you remember where it comes from, maybe you don't, but it comes from the idea of just like, right, this is a volume you can trace out in 3 dimensions. This is our little piece of a sphere, so in spherical coordinates, you need to use different lengths here in order to trace out that volume. Okay, so this has the correct units. That's good. Notice that this has units of meters cubed, which is the units of volume, okay? And in this case, when I vary r, theta, and phi, it traces out a volume, okay? Which is what I want. Okay, it's going to trace out this little bit of volume and eventually, right, a whole sphere. We're trying to solve this integral, a volume integral of rho r d tau. Now, we know we're going to do it. We're going to simplify, and we're going to do this volume integral in spherical coordinates, which means we're going to replace that d tau with this guy here. Okay, we've got our sphere here, and we need to figure out what the limits should be of our integral. Okay, well, in order to fully trace out the volume of the sphere, we need to take r, needs to go from 0, right, to our big R. That's the total radius of our sphere. Our d theta needs to go from 0 to pi. That'll take it, right, from here all the way up. Okay, 0 to pi. And then we need to trace our phi all the way around. Okay, so that will trace out our full sphere. Okay, if we were just doing a hemisphere or a portion of the sphere, our limits would be smaller than these, but we're doing the whole sphere, so that's what we get. Okay, so our integral ends up looking like this with the limits in there. And again, it's a volume integral, so I need to take 3 sets of limits. All right. We're going to take a simple case here. So we're going to assume that rho is constant. I'll give you guys a more complicated problem in your homework. But if that's true, then I can pull rho out of the integral. And you're probably thinking, well, if that was true, I didn't even need to take an integral. And you're right. It would be pretty simple to solve. But we'll save that kind of stuff for the homework. And now I'm rewriting this integral just to make it a little bit easier to solve. Basically, I'm taking the bits that depend on these individual limits, and I can evaluate these parts separately. So you end up getting rho. When I do the first part, I end up getting big R to the third over 3. Okay, hopefully that makes sense. The next one is easy. I just get 2 pi. Okay, and then the final bit, I'm going to get negative cosine of theta, and I got to take that from the limit of pi to 0. Okay, so simplifying that one more time. When I evaluate the limits on that last bit, I'm going to get 2, and I get the volume of a sphere, which is good, okay, times the charge density rho. Okay, and again, like you said at the beginning here, if rho is constant, you should know you just need to take rho times the full volume of the sphere to get the total charge. But, you know, we illustrated some things along the way, so that's okay. All right, so that's the answer to that problem. Okay, so we're going to do one more little bit in this video, and that little bit is going to be about how you transform an integral from Cartesian to cylindrical. Okay, that would be taking x, y, and z to our cylindrical coordinates, which are z, r, and phi. Okay, so let's draw a picture. Okay, I'm going to draw a cylinder. And well, we're going to make our life a little, it might be kind of hard to tell here, but this cylinder, I am going to center it, at least the center of the cylinder will be on the origin. Okay, so S here is going to be the radius of my cylinder. Okay, so that's, I'll write it down here. S is the radius. And then Z is the height, okay, or whatever you define Z to be. So again, we're trying to take a cylinder or maybe an integral that we would do in the XYZ coordinate system, and I want to do it in the cylindrical coordinate system. Okay, so let's think about what that means. Okay, the first thing you want to do is just be able to recast XYZ, okay, into our new coordinate system. Z is pretty easy. The Z in the cylindrical coordinate system is the same Z in the Cartesian coordinate system. Okay, if I look at my picture here and I define, let me pick a point on my cylinder here. I'm going to pick a point here. I'm going to define, let me do this in a different color. Here's a point. I'm going to define this angle to be phi. That's between a point on my cylinder and that x plane. Okay, then I get that x, this is this distance here that defines the point. Okay, x is going to be equal to s, that's the radius of my cylinder, times the cosine of that angle, phi. Y is going to be the other direction, that's s times the sine of phi. And now I need to think about what I would want to do if I wanted to trace out a little itty bitty volume of my cylinder. That would look like this. Okay, so this is, it's big, but imagine it's just a little piece of volume of my cylinder. So this is my d tau. Okay, if I think about it, this side's pretty easy. That's just a little height of my cylinder. That's dz. Okay, this little section here, make this color coded. This is dz. Okay, this little section here, that length is just dr. Okay, and then the last little bit is just to figure out the length of a little arc here. Okay, this is just going to be s, which is the radius of that point in the cylinder, times d phi. Okay, so that means that to trace out this little volume, instead of having a dx, dy, dz in my integral, okay, I'm going to have a dr s d theta dz, or another way to say that is d tau is going to be equal to s ds d theta dz. Okay, and this still has units of meters cubed because this has units of meters, this has units of meters, this has units of meters, this doesn't really have units at all, right? It's just radians, which is more like a label. Okay, I'm going to end it there. This video got a little bit long, but hopefully that helps you understand how to recast these problems in spherical or cylindrical coordinate systems.